All right, so today, as a continuation from our discussion from last time, we're going to be talking about inverse functions. We already talked about what it meant to be a one-to-one function. Remember, for a one-to-one function, just like a regular function, each input will give you one output. But if it's a one-to-one function, then that output can only be obtained from a single input value, so that you can basically, reverse engineer, go backwards. So if f is a one-to-one function, if f is a one-to-one function, then there exists an inverse function we'll call it g, such that, so keep in mind here that g is going to be the inverse function, and as we talked about inverse functions and the way inverse operations work, it's going to undo everything that the function f does. And the way that f and g are written, if you do composition f of g of x, you get x. Or if you do function composition in the other direction, you do g of f of x, you get x. So as we know from previous experiences with functions, if you were to plug some value into a function, like if I plug here x into g, g is going to do something that's going to change, potentially it's going to change what that input is into something new. If you then take that new value and you plug it into f, f says, okay, I see what you've done, now I'm going to go backwards and give you the original. Okay? I'm going to be able to tell you exactly what you plugged in at the beginning. Or if you plug the value into f, and f does whatever it does to the value, g can come along and say, okay, let me completely undo whatever you did. Okay? For example, if g happens to be the cubing function, what would f need to be to undo cubing? How would you undo cubing? Well, not square root, cube root, right? If g always adds 5 to your input, how can f undo adding 5? Subtracting 5. So you'd see these inverse operations going on between a function and its inverse. So, for example, I want to look at f of x is equal to 2x plus 4, and this is just the same kind of stuff you're going to see in your homework. And g of x is equal to 1/2 x minus 2. So I'm saying here are these two functions, and I'm going to ask the question, are f and g inverses of each other? And what you're trying to figure out here to determine whether or not these functions are inverses of each other is they want you to check this. If you plug g into f, well, everything basically cancel out, for lack of better words, to give you the original input x. And if you compose it the other way, well, things cancel each other out so that you still get back to x. So what we're going to do is just going to do each of these function compositions so you can see what this looks like algebraically. So I'm going to do f of g of x. So that means f of, and just to color coordinate these things like we do, this means f of g of x, which means I'm going to be replacing all of the x's in my original f function with f of x, with g of x, and g of x is 1/2 x minus 2. So this is the substitution that I'm going to make. I'm going to make it up here for this. Now, normally we would already have a numeric value that we'd be plugging into g, and then we'd plug that result into f, but here we're working with algebraic expressions, plugging one function into another one. So this is going to be 2 parentheses plus 4. And inside the parentheses where we had x is where we're going to be plugging in g of x, or that 1/2 x minus 2. So as I work this out and I distribute, what do we get? 2 times half x. Just gives you 1x. 2 times negative 2 is minus 4. And then there's the plus 4 that was there as part of the original function. And when you simplify all of this, what do we get? You just get x. So I plugged one function into another one, and everything reduced back to give me just x, which basically says whatever g would have done to that input value, f would then undo all of those steps by taking the inverse of each of those algebraic operations. Well, now let's go the other way. If I do g of f of x, so that means g of, I'll let blue be f of x. So I want to see what happens whenever I compose g with f of x, and f of x from above is 2x plus 4. And so in my function called g, I'm replacing all of the x's with 2x plus 4. So g was 1/2 x, I'm going to use parentheses, minus 2, and inside the parentheses, which is where my x was located before, I'm writing the 2x plus 4. This is more difficult than the function composition we had earlier, a few weeks ago, because we're having to plug variable expressions into other variable expressions. So now distribute this. What's half of 2x? Hopefully you know that half of 2 is 1, right? Okay, in case you did not know, half of 2 is 1. And now that you know, you're better for it. Keep distributing. Half of 4 is 2, and then of course there's that minus 2. And when you simplify this, you again get x. So for each of these compositions, when I did f of g of x, I got back to x. When I did g of f of x, I also got back to x. And so what we have shown, and then what we can conclude, is that f and g are inverses of each other. And in other words, g will undo what f does. G is the inverse of f. And so a lot of the time, the way that we express that is instead of saying g of x, and we're talking about a function's inverse, we'll use f inverse of x like this. Don't say f to the negative first power. That's not a power. This is read as the inverse of f. So f inverse of x, this is the inverse function.